Okay, so today's lecture is on capacitance and tan delta measurements. Basic concepts today we will cover. After this class, we will cover the measuring techniques actually. Until previous lectures, what we have covered is generation and measurements of high voltages. Now onwards, the topics related to the performance of power equipment will be covered. So the difference is, we have studied how the high voltages can be generated, and then how these can be measured in a laboratory. That we have studied. Now, applying that voltage, or to assess the performance of the power equipment, or assess the condition of the power equipment, or diagnose whether there is any problem or whether the equipment will survive for long or not. So that kind of aspects are covered now. So in this lecture, we will go through capacitance and loss tangent of power equipment or dielectric materials. What basically a power equipment consists of? A power equipment basically consists of a conductor which is insulated from a core which is at ground potential. That core sometimes maybe floating ground potential, maybe somewhere else, like the transformer where the mid winding is grounded. That is a different story. But in general, the power equipment consists of one conductor which is active conductor, we can say. The other one is ground, and in between insulation. So what the failure of the power equipment means what?
Insulation failure.
A failure of power equipment means the failure of the insulation which is insulating the conductor from the core or ground. For example, rotating machine, if you consider, then the stator core is at ground potential, stator winding at live potential, and in between there will be insulation like varnish and then Teflon or other materials, even paper or cloth can also be used. Even in the transformer, the same thing. In cable, if you see, the centrally there is a core or conductor which will carry the current, and then surrounding it there will be insulation, and then finally the final layer will be a grounded layer. Like this, every equipment has these basic three components, and in between that second component is insulation. Failure of this is equivalent to saying that the power equipment is failed. In fact, the fraction of cost of this is less only in power equipment actually. Cable, of course, it is major only, but if you consider any transformer or motor, so the cost is not so much compared to this one. But what is important is if it fails, then it fails. That's it. Power equipment fails. So what is the condition of a power equipment? How the condition of power equipment can be assessed? Since this insulation is important in the sense the quality of the insulation or the status of the insulation or the condition of the insulation is very important, because if it fails, the power equipment fails. So condition of the insulation is condition of the power equipment is assessed basically by the condition of its insulation. How the dielectric material is, what is the current status of that one, and how long it can survive. All these aspects are they boil down to the condition of the insulation. Okay, so but for the condition of the insulation, what are the parameters that need to be assessed. So that as part of that, in this lecture we will study capacitance and loss tangent. So power equipment basically, if it is tested, it is tested like live conductor is connected to one terminal and then the core is connected to other terminal. So we will be testing basically the condition of the insulation by connecting like it as a capacitor. It acts like a capacitor when we are testing the power equipment. The reason is we have to test like a capacitor only because we have to test the insulation material in between the conductor and the core. Okay, we should not test it like it operates in power system. It's not like that. So basically we will be testing the capacitance of the system, right? And what is the condition of that capacitance and all. Now in general, a power equipment can be under test can be approximated as a capacitance, a lossy capacitance under test. Right, now you can see this is non-ideal or imperfect dielectrics. Are there any ideal dielectrics? Ideal dielectrics are ideal dielectrics only, they don't exist. Right? So all are non-ideal only. So imperfect dielectrics. So what is the approximation? How do we consider them? Of course, this is circuit point of view we are giving, which is important for insulation engineers to understand. It is not a physics point of view. Otherwise, we would have introduced complex permittivity and then real permittivity. All such topics would have been introduced. Of course, they are also of interest, but as a practical engineer from engineering point of view, so this is what is important. So actually, this is the generalized dielectric between parallel plates, right? So it is basically a capacitor, a lossy capacitor. So like this, right? All capacitors are will be having some losses in them. So this lossy capacitor can be represented by two representations. One is parallel representation, other one is series representation. So in parallel representation, the capacitive portion, pure capacitive portion or ideal part of the capacitive portion is represented by a parallel capacitor Cp, and in parallel with a resistor, this is the non-ideal part. So this resistor is due to leakage of the current, you can say equivalently. Actually, there are different mechanisms for AC and DC, of course. What is the mechanism of AC? Loss mechanism of AC?
Polarization and dipole. Polarization and dipole moment.
Yeah, dipoles will tend to align and de-align in the direction of the electric field, which alternates with time. So what will happen when they align and de-align? So they will radiate some energy. That is the loss mechanism, basic loss mechanism in AC. And while in DC, so actually the lossy currents will flow. This is purely resistive loss, you can say. But in case of AC also, we can represent that loss with an appropriate, equivalent resistance like this. So this part of the loss will reflect in a current which is in phase with the voltage. And what about the capacitive part of the current? What does it constitute basically? will it be in phase with the voltage?
So out of phase.
It will be leading by 90 degrees.
It will be leading by 90 degrees. This current is a displacement current. Okay, in this, the current through the capacitive branch is displacement current, while this current through the resistor is lossy current, which is in phase with the voltage. So this is how the lossy dielectric or lossy power equipment can be represented in by two components, one capacitor and another resistor. While the capacitor is ideal part and then resistor is non-ideal part. Similarly, this is parallel combination. Then similarly, series combination is also possible. So in this, there is a series resistor CS, we have named it. So this ideal part corresponds to this actually. And then there is a series resistor which is a non-ideal part, lossy part. So in this case actually, the loss is associated with the capacitive current itself, the current displacement current itself. So it is flowing through the R also. So by this way we are actually having the total actual current having a relationship with V, with applied voltage V. There will be a different phase angle to the current than 90 degrees here. So, but of course, capacitor, across the capacitor, the voltage and current will have the same 90 degrees relationship, and across the resistor also they have same relationship, just in phase relationship. So this is a representation actually. So series representation. Equivalently, we can work out, and then formulas can be derived and everything will work out. So these two representations are there for non-ideal dielectrics. Apart from these two representations, series parallel also is possible. Now here, which is more appropriate for AC, which is more appropriate for DC, if we think physically closer relationship they have. So if you see the first one, parallel representation is more close to DC case, because in case of AC, the losses will occur. No? That lossy current actually due to the losses are due to alignment and de-alignment of these dipoles, which are actually, the losses are proportional to the displacement current to some extent, I square of that displacement current, because the alignment and de-alignment is related to that current only. So therefore it is more appropriate to have the losses represented in series with this capacitor actually. So therefore the second case, the series representation, is more close to AC case physically, and the parallel representation is more close to DC case. But of course, remember, any of the combinations can be used for any of the type of waveform by appropriately adjusting the resistor value. So the resistor value will change, but same each network can be used for AC or DC. For calculation purpose, you can use any equivalent circuit for anything. But physically, if we imagine, then the circuit A, the parallel representation is close to DC case physically, and the series representation is close to AC case. But a network of series and parallel representation both is suitable for complex networks like this. For example, like this. Now, in this case, we have, these are actually leakage currents or lossy currents, and this is actually displacement current only, polarization current, displacement current only. But this loss of this resistor it represents the losses due to AC component of the current. So this kind of complex networks network representation for a lossy capacitor is also possible. Now, for these basic equivalent circuits, we will see what are the quantities, capacitance, etc. Let us go through that one. Now, this is parallel representation. In this case, U is the voltage, applied voltage across the dielectric. Then I is the total current, right? And then this is IC, capacitive current, and this is resistive current. I should represent IC, capacitive current. This is resistive current. Then what is the phasor diagram of this one? So if you start with applied voltage U, then the current through the resistor is in phase with that one, right? So that's why the current is indicated like this, certain amount with I subscript R. So this is also same as I subscript R. This is also I R. Now, what is the capacitive current? Capacitive current will be 90 degrees ahead of this, right? So, or leading, 90 degrees leading. So, this is the capacitive current, which is 90 degrees leading IC. Then, this angle delta, which is the angle between total current I and the capacitive current IC. So this represents what? Suppose the delta equals to 0. Can you comment about loss?
Loss is 0.
No
Loss
losses.
is no losses. So delta increases, loss increases. So do you understand? So it represents how much resistive portion is there, or what is the ratio of resistive portion of the current to capacitive portion of the current. So actually capacitive portion of the current is useful current. Useful current means it represents how pure the dielectric is, how pure the capacitance is. And IR indicates the lossy portion, how much loss it has. And a ratio between IR and IC represents a relative loss. Relative means for this much capacitance, this much loss, something like that. So that's what we are interested to tell about the status or to diagnose the insulation condition. So now let us see what are these currents. IC is actually U by 1 by j omega C. It will turn out to be U into omega into C, magnitude. Of course, J will be there. So if you represent in phasor notation, this is the magnitude, U omega C. And similarly, IR is U by R simply. U is applied voltage divided by resistance value, R. Now tan delta is defined like this, IR by IC. From this figure only. Delta is defined like this means, and delta is defined by this quantity. So IR by IC, what it becomes? Simply use this quantities and then you will get 1 by omega CR, tan delta. So now tan delta represents what? Tan delta represents simply how much lossy the material is, how much lossy the dielectric is. Or if it is power equipment, how much lossy the power equipment is. It is the ratio of resistive current to reactive current, or resistive current to capacitive current in power equipment. Now phi, there is another angle phi. See, total angle is 90 degrees, right? U and IC. So if you subtract delta, the remaining angle is defined as phi. Now what is cos phi? You see, cos phi equals to IR divided by root of IR square plus IC square. That's total I. Right? Now equals to 1 by omega CR. What it is? What did I do? Okay, you have to do some small, simplification. Then it will become like this. 1 by omega CR divided by root of 1 plus 1 by omega square C square R square. Why that simplification is done? Just to represent cos phi in terms of tan delta, that simplification is done. Otherwise, you have to start like this: u by r divided by u by r whole square plus u by u omega c whole square. Like that you have to do. U square you have to take it out, and 1 by omega cr if you take out common, then it will become 1 by omega cr into 1 by root of 1 plus omega square c square r square. Now this is simply tan delta divided by 1 plus tan delta whole square, or 1 plus tan square delta. Now the value of tan delta, how much do we expect?
Zero, sir.
0 you expect. Then that is ideal material.
Ideal.
It will be between
Ideal
0 to
material
1.
does
Sir.
not exist. Huh?
It will be between 0 to 1.
0 to 1. 1 is, 1 means it is huge, right? Okay.
Yes, sir. Continue.
It will be less than 1 and close to 0 actually. So if that is the condition, then cos phi is approximately equals to tan delta. You can see. Tan delta is almost negligible, tan square even more negligible. So 1 plus something is 1 only. So simply it becomes tan delta. Cos phi equals to approximately tan delta if tan delta is less than 1. This approximation holds then only. Let us see by typical calculation. So this is oil impregnated paper details I am giving you. Suppose the dimensions are thickness 1 mm you consider, and A 1 meter square of area, means for example it is wrapped on a cable or something like that, or wrapped on a winding. If it is the thickness is 1 mm square and total area comes out to be 1 meter square, and the value of resistivity which represents the last component is 10 to the power of 11 ohm meters. So then the total resistance of that rho into T by A or rho into L by A, some people use L actually, so which turns out to be 10 to the power of 8 ohms for this case. And then similarly capacitance, if we calculate, the epsilon r is around 3.5, and then with epsilon, this epsilon naught you can show for the same dimensions it is 31 nanofarads. This is the formula. So if you calculate tan delta 1 by omega c r, right, for parallel representation, so it turns out to be 10 to the power of -3. Means what? How much? 0.001 tan delta. What are the units of tan delta? Hello?
Dimensionless, sir.
It is dimensionless because it is the ratio, right? Ratio of two lengths is always dimensionless. So tan delta is dimensionless. Now, this is around
But
0.02.
lossy tangent won't it be to be varied with frequency, sir? In case of impulse.
Yeah, it will vary with frequency. You are right. Tan delta value changes with frequency because all these values, permittivity, even resistivity, are functions of frequency. The equivalent circuit that is mentioned is valid for particular frequency. It is perfectly valid. If you want to make it frequency dependent, frequency independent, then you have to represent R and C, etc. In terms of frequency actually. So that complicates the problem. So whatever equivalent circuits we have studied, for a particular frequency, they will fit well, perfectly. For example, AC you are analyzing, DC you are analyzing, or combination of AC plus DC. AC means particular frequencies So for that, these equivalent circuits will work perfectly. But if you want to work for all frequencies, then the values actually will change with frequency. So the more accurate representation for physics-related studies, you should represent these R and C as a function of frequency. So it is a complicated study. But of course, for engineering approximation, you can assume resistor values within certain range and then capacitor value within certain range of frequencies, they will remain same like that. And engineering applications you can do. So, but for particular frequency, of course, these perfect circuits can be made.
Yes, sir.
Equivalent circuit. Now, for series representation, so the same analysis can be done for series representation also. In this case, the definition is a little bit different. It is not in terms of currents now, but it is in terms of voltages it will be. See, this is the current I through the circuit. See, in case of parallel representation, we start the phasor diagram with U. And in case of this, we start the phasor diagram with I, current I. Now, if current I is chosen, immediately the resistive portion of the voltage I into R is in phase with it. That is UR. This is the resistive part of the voltage, and this is the capacitive part of the voltage. So now again, the capacitive part of the voltage will be lagging it by 90 degrees. So this is capacitive part of the voltage. Now this triangle you have to form here, or total voltage is UC plus UR. This is the total voltage U. This voltage is making an angle delta with capacitive voltage. So this is how delta is defined. Exactly same actually it should be. So tan delta is now UR by UC, or resistive voltage divided by capacitive voltage. Resistive voltage divided by capacitive voltage. Earlier, resistive current divided by capacitive current. So in this case, it is like this, and then the resistive voltage is I into R, and capacitive voltage is I by omega Cs. Then it becomes omega Cs into R. So what is the difference here? See, remember the series, in the series representation, small r and Cs are used. And for parallel representation, capital R and Cp are used. Now here, the tan delta is omega Cs into R. Earlier it was what for parallel circuit?
1 by omega C.
It was 1 by omega Cp into R. So how can it be? Whether the units will not change. Sometimes it is 1 by omega Cr and now it is omega Cr. Both are dimensionless quantities. That's why it appears in, whether it appears in numerator or denominator doesn't matter. Both are dimensionless quantities. 1 by omega Cpr, also omega Csr. Now here, so both must be same, right? So now let us see. Now which is maximum, which is more and which is less? If you compare capital R or small r, it is intentionally represented by this because capital R will be high value, small r will be small value actually, because small r is in series, right? In series with the capacitor. So entire, in this representation, entire current through the capacitor, displacement current, also should flow through this resistor R. Therefore, the resistance must be kept less in order to match the loss component, losses. And in case of parallel this thing, so the resistor current should be small because losses normally will be small. So that's why the resistance value is more in case of parallel representation. So somewhere some sound is coming.
Sir,
Hello?
hello, sir.
Are you able to listen to me? Some sound is coming.
Hello, sir.
Hello.
Yes, sir, I'm saying that in series combination, tan delta is directly proportional to omega.
Just 1 minute. I am unable to listen to you. Repeat.
I'm saying that in series combination, tan delta is directly proportional to omega.
But
In series combination, tan delta is directly proportional to omega.
but that is valid only for particular omega.
Yes, sir,
Okay.
particular omega. But if you take consider this circuit for DC, then tan delta becomes 0. We get a perfect dielectric. Na? This circuit is good for DC case. I'm thinking.
Which one?
Series combination.
Series combination good for what?
DC case.
Huh?
For DC case, sir.
DC case?
Yes, sir. I'm asking that.
No.
Sir, because if directly proportional to frequency, if frequency is 0, then tan delta is 0, then we get a perfect dielectric. Sir.
No, actually, for DC case, this tan delta is not defined for DC actually. Okay. It is for a particular frequency it is defined, and for AC. So DC case, the lossy representation is only for representing the losses. Okay, that equivalent circuit is used for circuit analysis. But tan delta is not defined actually for DC. Tan delta is defined for power frequency and other frequencies, higher frequencies. Normally we refer to power frequency only. Some noise is coming from somewhere. Hello?
Yes, sir.
Whose mic? I don't know. It is some noise is coming.
It was coming from Dhawal's mic, sir.
Dhawals only. Okay. Oh. So you switch on only when you speak. Okay.
Yes, sir.
So tan delta of course will change with frequency, but it is referred mostly for power frequency only. because all the power equipment will work for power frequency and losses are referred to power frequency only. Of course, frequency dependent characteristics will be assessed sometimes, but in specifications, power frequency specifications will only be there. That when I said this equivalent circuit it is suitable for DC, so actually the power equipment analysis, for example, lossy currents and then voltages and electric field distribution inside the cable. So for all such analysis, we do use equivalent circuits like this. So in that case, the best equivalent circuit for DC is given by this one, which is close to that one. For example, if there is no frequency related current, suppose if I use the second equivalent circuit and then apply DC, what will be the current? Suppose if I use series equivalent circuit and apply DC, what will be the current through the this equivalent circuit?
In steady state it will be 0, sir.
This is the problem. So in steady state there will be no current. Then, but that means that there is no loss.
Yes, sir.
So if you represent using series combination, then you cannot perfectly represent the DC case, because
Sir,
DC case also losses exist.
We want the capacitor to unlossy, sir? Because capacitor phenomena is that to charge instantly. That's it only, sir.
You want, but it will not exist like that. I also want capacitor to be perfect capacitor.
So
Okay.
if you go for the parallel implementation, as you said that it is used for DC combination. So as we go for the parallel representation, then we get a tan delta is equal to 1 upon omega RC. If you put the frequency there 0 for calculation.
No. You should not put 0. Say you should not put 0 and then say tan delta is infinity for this one. Tan delta value you have to assess at 50 degrees, 50 hertz for comparison purpose. Okay. Representation of the equivalent circuit is a different issue. Representation of an equivalent circuit for this is not only for tan delta and capacitance measurement. Okay. So representation of equivalent circuit for several purposes. For example, I am telling you, when we find out internal potential distribution of a power cable, suppose. This is an example I am telling you. Of course, it is applicable to power equipment also. Any power equipment, transformer or whatever it is. So, suppose I am considering a cable. I will give the example of that one. You have asked an important question only. So here, this is my central conductor of the cable, and surrounding this there is an insulation. And then again, of course, outer layer which is at ground potential. And here this is U, some potential U. Now this cable has to be represented by an equivalent circuit. Equivalent circuit means cable itself can be approximated with the equivalent circuit. The dielectric can be approximated with equivalent circuit. So what I mean to say that in using for AC case and DC case, the two extreme circuits whatever are given are suitable. DC case. If in DC case, if you represent all the dielectric material by only series capacitance and resistance like this is I am drawing only 2 here. Actually around 100 such units each layer like this is represented by one capacitor and one resistor like that. So 40 to 50 or 100, one of my student is working on this actually. So this kind of representation if we do, then you will get at different nodes different potential. Right, that's how potential distribution inside the cable can be assessed. So this is one of the techniques. All the power equipment also can be approximated like this. Now in this case, if I represent with the series capacitance and series resistance only, I cannot perfectly represent a DC cable, because in DC cable, when I apply DC also there will be loss. But that loss, how to represent that loss? So I cannot represent by a series resistance, it's not possible. So when equivalent, if I say that I am representing a lossy capacitor with an equivalent circuit, that equivalent circuit should be perfect enough to represent all the phenomenon, right? So now, in case of DC, whatever losses are occurring in the cable, I am unable to represent using series capacitance and series resistance type of approximate or equivalent circuit. So ultimately, I have to use a parallel resistor for this in order to represent the DC losses. DC also losses will be there. Okay. So that's why in equivalent circuits, when I say series circuit is more suitable for AC case, because AC case the loss phenomenon is also related to displacement current I. But in DC case, there is the loss phenomenon is related to leakage current which flows through the dielectric, across the dielectric. So therefore there must be a parallel resistance. That's what I said.
Okay, sir.
Right. Now between terminals the impedance is same. Okay. See, for a particular frequency, and when omega is not zero, I should be cautious now. Omega is not equal to 0. Of course, if omega is equal to 0, can I divide by capacitive current? Can I divide resistive current by capacitive current? Let us go back and see. So here, capacitive current is 0. Capacitive current is 0. So this basic definition itself will not work for DC, you can see. IR divided by IC, something I cannot divide by 0 because it will be undefined. Now, between the terminals, the impedance is same. Impedance is the same because whether it is series representation, whether it is parallel representation, the impedance must be same, right? So, for the equivalence of those two circuits at a particular frequency omega, which is not 0, then we can write like this. The parallel impedance of the parallel circuit is Zp is equal to Zs, the series impedance of the series circuit. What is Zp? Zp is R into 1 by j omega Cp, that capacitive impedance, divided by R plus 1 by j omega Cp, which is equal to series resistance R plus series capacitive impedance 1 by j omega C. Now, equating these two, we will get this kind of equation. R by 1 plus j omega Cpr equals to R minus j omega Cs. Now, real part and imaginary part can be separately equated also. So, it is, by multiplying numerator and denominator by 1 minus j omega Cpr. So, we will get like this. Then R, the real part of the resistance this side is equal to real part of the resistance this side. So which is equal to R equals to R by 1 plus omega square Cp square R. Now in terms of tan delta, if you write R into tan square delta by 1 plus tan square delta. Now tan delta itself is 0.001, just now we have seen. So tan square delta is how much? 0. Again 0.0000001. Right? It is very small. So therefore, this is the order I have written. Please do not conclude that for every material it is 0.001. It is in the order. In this order it will be. So 1 plus very small quantity, this can be almost neglected, and this becomes 1. So therefore, small r is equal to capital R into tan square delta. R equals to capital R tan square delta. Now tan square delta is very small, you know. So small r is very small compared to capital R. Capital R multiplied by very small quantity gives you small r. So this you may remember, R equals to R into tan square delta. And then Cs by Cp. Similarly, equate the imaginary components also. You will get like this. Omega square Cp Cs R square is equal to this one. From this Cp Cs by Cp, take it out. This becomes omega square Cp square R square is equal to 1 plus omega square Cp square R square. This omega square Cp square R square, you take it this side. So that becomes 1 plus 1 by omega square Cp square R square. Then that is 1 plus tan square delta. So Cs by Cp is equal to 1 plus tan square delta. What message does it give?
If tan delta is very less than 1, then both are equal.
So series capacitance and parallel capacitance are more or less same. That message this gives. But resistors are not same. Series resistor is R into tan square delta, very small. So series resistor is very small. Because it comes in series, so it takes huge current, just like the series capacitor. So when you have taken huge current through the resistor, so obviously the resistor which represents losses should be small. So that's what it will happen. But the capacitance is almost same. Series capacitance and parallel capacitance is almost same. So this is the equivalence of two circuits at a particular frequency omega, non-zero. Okay, do you have any questions?
Sir, in the previous slide where the real parts were equated, the
Yeah.
R equal to R by 1 plus omega square Cp square into R square, no, sir?
R equals to?
Small r equal to R by 1 plus omega square Cp square R square, no?
This is R square. Yes, you are right.
So in numerator, how do we get tan square delta, sir?
Numerator, how do you get a tan square delta?
Like this will be R by 1 plus tan square delta.
Just wait. It is actually 1 by
Yes, sir,
1
yes,
by
sir.
omega square Cp square R square, right?
Yes, sir, got it.
You take it out, okay. Omega square Cp square R square, you take it out common. So it will be R by omega square Cp square R square divided by 1 plus 1 by omega square Cp square R square. Yeah.
Yes, sir. Thank you.
Yeah, any other question?
So if a void or hole or something is present in a dielectric, and then it also forms a resistive part.
It also
form a resistive part, sir.
It also has a resistive part, it also has a capacitive part, yes.
So how it will connected to in between lossy dielectric? The series of parallel or both can be.
See, if actually for when voids are there, we have to consider partial discharges. That will be one of our next topics. But I can give you the circuit here itself. Suppose this is the capacitor and there is a void here. Okay, so its equivalent can be represented like this. Now consider the portion of the dielectric like this. Suppose the void is, assume that it is spherical. That makes you, thinking, understanding very easy. So here, assume a spherical cylinder like this, just, up to the diameter of the void. So rest of the portion you ignore. Rest of the portion is represented by a capacitor or in parallel with resistor. Rest of the portion of the dielectric I am saying, except for the void. Now void portion you can consider here the upper portion, again same representation. Of course, it is a parallel combination or series combination. And bottom also same way, you can represent one capacitor and one resistor in parallel. And here also, this void also, if I draw the void like this, you can represent it by a capacitor and a resistor. This resistor is actually representing the loss through the dielectric, whichever void may be gas, maybe vapor, or maybe air.
Only permittivity will change, sir, no? Of this word capacitor.
Equivalent capacitance will change.
Okay.
But it can be represented. Ultimately, it becomes, a circuit like this only.
And then we have to calculate the equivalent of all that.
Yes, equivalent you can calculate. But we will study what are partial discharges, etc. that will occur inside these voids actually. Actually, power equipment is supposed to get damaged due to these kind of voids only. Of course, there are many popular theories. So, some people will say this is the reason for failure, or, protrusions from the, electrodes, or, treeing. It depends on the material also. Those concepts we will study. Any other questions?
Thank you so much. Thank you.
Okay, then we will continue.